Okay, I'm probably gonna give some people like 1 or 2 more minutes to show up, and then if not, we'll get started. Um, we might have an interruption today in our lesson just because SpaceX is launching their SN8 Starship, which is a pretty historical moment. So if they do end up launching it because they scrubbed yesterday, we'll probably take a short break in the lesson to watch it. Okay, around 2:02, I'll probably start. Okay, actually, apparently the launch has been already pushed closer to the end of their window, so it'll be after our lesson for sure. Okay, I guess we can get started then.
Hey, Biscuit.
Yep.
Do we have the attendance bot running, or do you want me to take attendance?
Vlad said he would take a screenshot at some point, but
Okay.
I suppose you can as well. No harm in
Sure,
it.
sounds good.
Okay. So with that in mind, let's get started. This is the first lesson in a series that Vlad and I are going to be running just on the definitions and fundamentals of rocket propulsion and rocket theory. So yeah, I'll be doing the first lesson this week. Vlad'll be doing the next lesson next week, and after that, we'll have some more lessons on aerospace in general. So yeah, this is the first lessons in a series of 2 on the theory of propulsion, and it will only provide an introduction, of course. Rocket science is a very complex field with lots and lots of math, so we can't really go super in depth, but we'll try and make our lessons as beginner friendly as possible, and if there are any things you need clarification on, feel free to ask lots of questions. And both of these lessons will cover the majority of Chapter 2 of George Sutton's Rocket Propulsion Elements, and this textbook is available in the Rocketry Resources channel. We have like a link to a PDF there. So, yep. With that in mind, let's get started. So some of you guys who've taken grade 11 or grade 12 physics will probably be familiar with the concept of a force. So in physics, a force is any interaction that, when unopposed, will change the motion of an object. So yeah, that should be pretty intuitive. Like imagine, you have like an object on like a frictionless surface, like maybe like ice, and you push on it. Well, it'll start moving, right? And maybe it's already moving, and you push on it, and you can stop the object. So yeah, when an object is when you put a force on an object and the force is unopposed, it's important to realize that yeah, it'll change the motion of that object. So more specifically, there's Newton's second law, which actually relates the net force experienced by an object with the acceleration. So this law basically states that the force is equal to the mass of the object times the acceleration experienced by the object. So yeah, in terms of units, mass has units of kilograms, and acceleration has these funky units of meters per second squared. So yeah, it means like meters per second, right? Acceleration is telling you how the velocity is changing. Velocity is meters per second. So yeah, it's meters per second over time, so meters per second squared. And thus, the force has units of kilograms times meters per second squared. And this unit is called the Newton, in honor of Sir Isaac Newton. Uh, yep. So now we'll do a quick example problem just to kind of solidify these concepts. So let's say you have a 2 kilogram block lying on a frictionless surface, maybe like ice or something like that, and you apply a 10 Newton force onto it. How fast will the block accelerate? So we just plug them right into our F equals ma equation. So we have a 10 Newton force, and that's equal to 2 kilograms times whatever acceleration the block experiences. So we just solve for A. A equals 10 kilograms per meter squared. I just substituted in the units there for the Newton. divided by 2 kilograms, and then this should say A equals 5 meters per second squared. I forgot to actually do the division here. So yeah, should be pretty clear how that works. Yeah, something else to mention actually quickly. Technically speaking, force and acceleration are something called vector quantities, but if some of you guys haven't seen vectors yet, that might be confusing. So for now, we'll just treat them as just numbers. But yeah, in grade 12 for sure, physics, you'll treat them as vectors. So now that we're armed with the definition of force, we can look into impulse. So impulse is defined as the integral of force with respect to time. And yeah, here's the formal definition. But this is like the mathy definition. The intuition is more important. So in regular terms, this means that the impulse is the area under a force-time curve. So if you have some curve like this, and this shows the force experienced by an object at each time frame. So some object, in this case, it would be experiencing like no force at time 0. Then at time 20, there would be 100 Newton force on it. And then at time 40 again, it would be experiencing no force. So some graph like this, the impulse is the area under this curve. So whatever this area here is, I'm kind of putting the pointer in. And yeah, the object's force time curve tells you the force experienced by the object at a given time. Yep. So now an important thing to notice is if the force is constant over the time frame, then the area under the curve is just a rectangle. So the impulse would just be whatever force it is times the change in time, right? That's just the area of a rectangle here. But yeah, important to remember that this only works if the force is constant, or roughly constant. Okay, great. So now we have kind of an intuition, kind of a mathematical definition. But this is a better definition that I found, which is much more intuitive to me. So it's that impulse can also be thought of as the change in momentum of an object. So you should be familiar with momentum already, just kind of from daily life. But in a physical sense, the momentum of an object is defined as the product of its mass and its velocity. So yeah, like a car, for example, it's pretty heavy, so no matter what rate it's moving at, it has quite a bit of momentum. But a car moving at like 10 meters per second will have less momentum than a car moving at like 100 meters per second, right? And like similarly, like even a tennis ball, like at 100 meters per second, will have less momentum than a car moving at 100 meters per second. So it's kind of intuitive how momentum works. And then impulse is just the change in momentum. So if you have some final momentum here, mass final times the velocity final, subtract the initial momentum, the initial mass times the initial velocity. That is the total impulse experienced in this time frame here. And then yeah, this formula is very useful if you know the initial and final momentum, or alternatively like the masses or velocities, that's the same thing, of the object. So here we have a quick example problem. So let's calculate the total impulse of an object with the force time curve from earlier. And then you can just notice that this curve can be thought of as just two right triangles, right? So you can kind of see how these things would be right triangles here. And they both have a height 100 newtons and lengths 20, right? From here to here and from here to here. So the area is just 2 base times height over 2 for each triangle. And then that just gives you 2,000 newtons times seconds. So then it's important to notice here that impulse actually has units of Newton seconds, which is a little funky, but yeah. And then here's an example using the change in momentum formula. So a rocket initially weighing 1 kilogram is launched at Cape Canaveral, or the Kennedy Space Center. At the end of the burn, the rocket weighs only 200 grams, but is moving at 600 meters per second. What is the total impulse of the rocket motor? So the initial momentum, we can figure that out. It's just the mass times the initial velocity, which is 0. It's at a standstill. So it has 0 initial momentum in this frame. And the final momentum is 0.2 kilograms. So yeah, important to convert your units into something standard. And then times the final velocity. So that gives you 120 kilogram meters per second. Thus, the total impulse is 120 minus 0 equals 120 Newton seconds. So yeah, that kind of shows you the difference in momentum formula for calculating impulse. So actually, does anyone have any questions in terms of impulse before I move on to specific impulse? Uh, don't see any questions in the chat. You can unmute as well, I guess, if you have anything you want to add. Nope. Okay. Yeah, you can DM any of the execs at any time, and we can also answer some questions for you. Okay. So I guess next thing we'll explain the concept of specific impulse. So specific impulse is denoted by IS or ISP, and it's defined as the integral of force over the gravitational constant. Yeah, I'll talk about that later. Divided by the integral of the mass flow rate, both with respect to time. So again, if you remember from earlier, this top integral here is just the total impulse, and then this integral here just represents the mass of the propellant of your rocket. So in other words, the impulse, the specific impulse of a rocket engine is the total impulse divided by G naught, which yeah, I'll talk about it later, times the mass of the propellant of the rocket engine. So it's defined as the thrust per weight of the propellant. So it's important to realize that this is just mass. Mass is different from weight in physics. So yeah, mass is like the actual amount of matter in an object, but weight is like the force experienced by an object due to gravity. So if you want to get weight at Earth's surface, you have to multiply the mass in kilograms times g naught. It's just some constant, and that will give you the actual weight of an object. So yeah, that's something confusing, I guess, for people who haven't seen forces before. But yeah, just bear with me. And so yeah, basically, ISP is like the miles per gallon equivalent for rockets, and it indicates how efficiently a rocket motor uses its fuel. So basically, a higher ISP means that a motor produces more thrust for some weight of expelled mass. And so yeah, that should make sense, right? Higher ISP means the numerator is bigger, so and yeah, you want your motor to produce more impulse. And then, or yeah, smaller denominator as well means less propellant mass. Yeah, means your rocket motor is more efficient. So an interesting note, ISP has these weird units of seconds. So if you remember, impulse has units of Newton seconds, and then this is weight, so it's force. So this has units of newtons. So you have Newton seconds over newtons, which just leaves seconds. So yeah, it's a weird quantity in that sense, but yeah, if you think about it, like the efficiency of the rocket, it should make sense. So here's a quick problem. We have the same thrust curve from earlier. If the mass of the propellant expended by the motor with this thrust curve is 800 grams, what is the ISP of this motor? And then, yeah, just assume G naught is 9.81 meters per second squared. So we'll just plug that right into the formula. We remember from earlier that that thrust curve has an impulse of 2,000 Newton seconds. Therefore, the ISP is the impulse divided by G naught, which is 9.81, times 0.8 kilograms, and that'll give you 254 seconds if you compute that. So here's an actual rocket motor. It's a model rocket motor. It's called an Estes A10PT. A is just like the class. It's the base class, so it's not very strong. And I'm not sure what these mean, but it's just like some other details. So here is force and here's time. So you can see produces over 10, almost like it looks like 14 newtons of force at peak, and then it kind of drops down. And then the impulse, the total impulse of this rocket motor is 2 newton seconds. And then the fuel weight was about 0.0359 newtons, so pretty light. And that gives you a specific impulse, if you run the math, of 57.9 seconds. So here are so now we know how to compute ISP, but what does it mean? What is like a typical ISP value? How does it compare to other motors? So here we can kind of see a graph of some different ISP values that's on this axis here, and then the thrust. which is on this axis here. So 10 newtons of thrust is like it's basically the same weight as a 1 kilogram weight, right? So you can kind of see, yeah, just how different propulsion systems fare. I can kind of give you a second to look at that, and then I'll explain what that means. So yeah, basically chemical propulsion, which you can see along the bottom here, has apparently the worst ISP out of like pretty much every type of propulsion, right? But the reason why chemical is still used so much is because it produces the most amount of thrust for like yeah, it just produces the most amount of thrust in general. Like all these other types, like ion propulsion, magnetic propulsion, etc., they have really good ISPs. They're very efficient, but they produce almost no thrust. Right, like 1 kilogram. Like satellites can weigh tons. It wouldn't be able to move the satellite. But they do have uses in something called. So basically, when you have like a satellite in orbit, the orbit decays over time because of like atmosphere and whatnot. So you need some way of like keeping your your satellite up, and then yeah, people use ion thrusters to do that. Vlad would probably explain more about that, or someone covering like orbital mechanics. But yeah, chemical is really the only type that scientists have actually managed to like actually viably fly rockets with. And then you can see how they have ISPs from around 200 to 450, and then they can produce like yeah, way off the chart numbers of thrust. Okay, so the next quantity we'll get into is the effective exhaust velocity, and it ties in really close to the ISP. So in real rocket motors, the exhaust velocity, like of the product shooting out the bottom of the rocket, it's not uniform over the entire exit nozzle, but it can still be useful to define some constant, which represents like the average velocity, and this is referred to as like the mass flow rate determined exhaust velocity. And so it's defined as the following. The effective exhaust velocity c is defined as the ISP times the gravitational constant g naught, and this can also be represented as the thrust force divided by the mass flow rate at some unit time. And notice that c and ISP actually only differ by a constant factor, g naught, 9.81 at Earth's surface. And yeah, c has units of meters per second, and Russian literature tends to use C versus ISP for some reason. But yeah, the key thing to note here is that they represent the same thing. You know, a better C means that your rocket motor is more efficient, higher C, and a lower C means it's less efficient. And yeah, it's just C, I guess, is more like it makes more physical sense because technically it's like the exhaust velocity of the rocket. In reality, it's a bit like the actual exhaust velocity is much lower because of the atmosphere, but like theoretically speaking, if there were no atmosphere, it is accurate. Like it is accurate in a vacuum, for example. So we'll do a quick example problem here. So here's the same motor from earlier, and we want to calculate this effective exhaust velocity. Um, yeah, based on the data provided. So we know our impulse, specific impulse, fuel weight, but we really only need the specific impulse, right? And so it's a very simple calculation. Um, yeah, you remember I gave you guys a mass flow rate formula, this one here. This isn't really used too often because it's very hard to measure for most engines. And yeah, we don't have the data anyway, so it doesn't matter. We'll just use the ISP times G naught formula. So yeah, we have that the ISP is 57.9 seconds. Thus, the effective exhaust velocity C is 57.9 times 9.81, which is just 568 meters per second. But yeah, like I mentioned earlier, due to the atmosphere, the exhaust never reaches this speed. It's much lower because, yeah, the exhaust collides with the atmosphere and slows down quite a bit. Let me check if we have any questions, actually. I don't want to leave people hanging. Nope. Okay. So, next constant we'll define is called the mass ratio. The mass ratio MR is defined as the final mass divided by the initial mass of a rocket. So yeah, mf is the final mass of the rocket after firing its engines, and m0 is the initial mass of the rocket. And this can vary anywhere from 60% for tactical missiles to 10% for like first stage rockets that are just meant to accelerate a payload. So MR can be calculated either for one specific stage or a whole rocket, or maybe even just like the motor itself without any payload attached or anything. So it's very versatile, and it comes up a lot when you're talking about like the whether a rocket will even fly. But I guess we'll explain this more in the final problem. The propellant mass fraction, it's defined with this weird Greek letter zeta, and it's used to represent, the zeta represents the quantity. I don't know why they chose this weird Greek letter, but it's basically the mass of the propellant divided by the initial mass of the rocket. And like the mass ratio, the propellant mass fraction can be calculated for an entire rocket, a single stage, or you can even just calculate it for the rocket motor on its own. And it's the propellant mass fraction. If you calculate it just for the rocket motor, it's actually a metric of the quality of the design of the propulsion system. Because if you think about it, a higher propellant mass fraction means that less of the propulsion system is like dead weight, and more of it can be allocated to just like actual propellant, which is what gives you energy. It's what accelerates you. And then, yeah, one last quantity we'll talk about is the thrust to weight ratio. And it's defined as the thrust of the rocket divided by its initial weight. Important, not mass. It's weight, where at Earth's surface, its weight is defined as mass times g naught, where at g naught is 9.81 meters per second squared. So the thrust to weight ratio specifies the acceleration in multiples of gravitational constant at Earth's surface, aka g's. You might have heard of like g-force, and that's like a similar concept. That a rocket can accelerate at when fully loaded. So, chemical propulsion has the best thrust to weight ratio of any currently viable propulsion method, which is why it's used. And it has thrust to weight ratios upwards of 100, which is crazy. It can provide 100 times the thrust of the weight of the propulsion system itself. And yeah, ion thrusters have thrust to weight ratios around 10 to the negative 5, which is why they can't be used to take off from the Earth's surface, like I mentioned earlier. But because they're so efficient, they still have uses in orbital maintenance, like preventing orbital decay. So yeah, here are some typical ISP and thrust to weight ratio values. So yeah, we can see here, chemical varies from about 200 to 468, but it has thrust ratios up to 100, which is very good. And yeah, the propulsion duration is never more than like a few minutes, right? And then there's some other ones, but stuff like, electromagnetic or ion, they have very high ISPs, like crazy 5,000 ISPs. But if you look at the actual thrust to weight ratio, it's like, 10 to negative 6, 10 to negative 4, that's like less than a percent thrust. But they can be active for months at a time. So then finally, we'll get into an example problem. So we have some motor X, which has an initial weight of 5.5 kilograms, and it contains 4.5 kilograms of propellant. And then the motor is fired, and then the thrust is measured. And then the following curve is produced by the sensor. So you can kind of see, it starts off with no thrust, then as it picks up pressure, it goes up around t equals 4 seconds. We have 800 newtons of thrust. Then we go up to 1200 newtons at 8 seconds, and then the motor dies off, runs out of propellant, and then goes to zero thrust. So it's a two-part problem. The first part is to calculate the total impulse, specific impulse, propellant mass fraction, and peak thrust to weight ratio of this rocket, of this motor. And then if the engine is carrying a payload which has a mass of 20 kilograms, calculate the mass ratio and peak thrust to weight ratio of the entire rocket with the payload attached. So first thing we'll do, we'll jump into part A. We'll calculate the total impulse of the motor. So this is done by integrating the thrust time curve. And this area is just 3 triangles in a rectangle, right? So you have this first initial section here, and that's just a right triangle. And the second part here, it's just another rectangle here. plus this little triangle on top, and then the final downslope is another triangle. So, we just have our formulas here, just basic area of a rectangle, area of a right triangle, and then we get total impulse of 8,000 newton seconds. And then we can use this to solve for the rest of the values. So remember, the specific impulse is just total impulse divided by the weight of the propellant. Thus, ISP is 8,000 newton seconds divided by 9.81 G naught times 4.5 kilograms, which is the mass of the propellant. And we get a ISP of 181.2 seconds. And the propellant mass fraction is just the mass of the propellant over the total mass of the motor. So we have 4.5 kilograms of propellant divided by 5.5 kilograms for the rocket, and that gives us 81.8% for the propellant mass fraction. That's pretty good. That means, only about 18% of the motor is like dead weight. And then, the peak thrust of the rocket is 1,200 newtons. If you look at the curve, 1,200 newtons is the peak right there. And therefore, the peak thrust to weight ratio is just 1,200 newtons divided by the weight of the motor, which is about 22.2. And that's good. That means you'll be taking off, right? As long as your thrust to weight ratio is greater than 1, that means you have more thrust than your weight. So you'll be able to take off, and you're okay. Now let's look at part B with the payload. So the mass ratio is just the final weight of the rocket divided by the initial weight. So the total initial weight of the rocket with the 20 kilogram payload is 25.5 kilograms, and the final weight is 25.5 minus the weight of the propellant, which gets expended during flight, and you're left with 21 kilograms. Thus, the mass ratio is just 82.4%, which is actually pretty high. You have a crap ton of mass for, just like a tiny little bit of propellant, like 17% basically, 17.6. So that's kind of concerning. And then the peak thrust to weight ratio of the whole rocket, again, 1,200 newtons divided by 9.81 times 25.5 kilograms for the rocket is actually only 4.8. So again, you are able to take off, but that's getting pretty close to 1, which is not good. And that's pretty low. Typically, you would use a much larger rocket to transport the payload. Otherwise, you wouldn't be able to get to any type of altitude with such a low ratio. So that's pretty much it. Thanks for watching. Next week, Vlad will cover the rest of the chapter, and he'll also touch on some other stuff, like lift, drag, etc., aerodynamic forces and whatnot, because there are a lot of different concepts when it comes to rocketry and what rocket engineers consider when they build their rockets. So feel free to message either of us if anything is unclear. And thanks everyone for meeting. I guess I'll take any final questions. If not, you're free to go. And a recording will be up on YouTube later today, so you can review this if you need to.